This video is a brief introduction to EQR Opt for CST Design Studio. EQR Opt is a optimization module that works in conjunction with CST Design Studio, and it looks for a Chebyshev transfer function in the passband of a filter. So this is a dedicated filter optimization program instead of using a general purpose optimization. So we have an equivalent circuit here of a comb line filter. These are resonators less than a quarter wavelength long. We bring them into resonance at band center using these capacitors, and then we have coupling capacitors between the resonators to control the coupling level. At the input and the output, we just have transformers. In the real filter, this might be a tapped input and output, but this output transformer is fixed and it sets the return loss level of our filter, and this transformer is allowed to vary. And in the end of the optimization, because we have a symmetrical structure here, it should have the same value as the one we set at the output. If we look at the frequency response of the filter as it sits, it's an n = 5, so we expect to see 5 distinct nulls across the passband of the filter. And here we have maybe 4 visible, and clearly the return loss level is not optimum. So if we turn on the optimizer, there's very little to set up here, only a few options and parameters. The key thing is really back here in the schematic. Here we've defined 5 frequencies, and these are the frequencies of the return loss nulls for the filter. The outer 2 are set by the user, and the software does not modify those. So these outer 2 set the bandwidth and the center frequency of the filter. And the inner ones are determined by the optimizer, and the fact that there's 5 frequencies here also tells the optimizer that it's looking for an n = 5 filter. So that's all that's required. We don't actually look at any optimization goals that are set up in Design Studio because we don't have to. We don't need those goals. So if we hit the button and start the optimization process, it's going through all the variables and determining the sensitivities, and now it's made its first step in the optimization. Because it's an n = 5 filter, we need 2 times n variables, so that's 10 variables in this case. So we have the 5 resonator capacitors, the 4 coupling capacitors, and the input transformer, which makes 10. And after just 3 iterations, we're already seeing a very nice passband response. And it'll go just a couple more iterations to try and make it a little more perfect. So it's done with the initial optimization, and now it's looking at the position of the poles and fine-tuning those pole positions just a little bit. And we're done. So in only 7 iterations of EQR Opt, we've taken a fairly coarse starting point and produced a filter with almost an exact equal ripple response in the passband. Now, if we're fine-tuning our design and we want to shift the bandwidth a little bit or shift the center frequency, all we have to do is go back to this list of frequencies and modify the outermost frequencies. We don't have to change any other return loss goals or uh, goals in the stop band of the filter. It's really only these frequencies that control the optimization. So let's make the upper frequency goal 10 megahertz higher. And if we do an initial simulation, of course nothing changes here yet, but if we start the optimization, we'll see it modify the design and move that upper band edge higher. So it's zeroed in on the upper band edge now, and after one more iteration, it'll go back and look at the pole positions and readjust those pole positions to make it equal ripple. And that's started now. And it will do maybe one or two more iterations. So here's our new design with a new bandwidth. Once we capture the passband of the filter, making these fine adjustments on center frequency and bandwidth are quite easy and quite fast to do. So now, what if we want to modify the return loss of the filter? What if our goal is really closer to 20 dB rather than 25 dB, which is where we're at now? So what we need to do is go into the schematic and modify the output transformer. It's currently at 4.4, the turns ratio. Let's make it 4.6. And if we re-optimize, we can watch it now change the return loss level. We need to change the plot back to dB. There we go. A change in return loss level is actually fairly large because all the element values have to change in order to bring us to a new return loss level. And we're getting close to 20 dB. Let's make one more step in that transformer. Let's go from 4.6 to 4.8. And that should bring us closer to 20 dB. And again, it's changing the plot. There we go. We're back to the dB plot. I've added a little parameter scaling here just to be safe. When we're optimizing a filter, often the first corrections that are computed by the optimizer might be a little bit too large, and the optimization can diverge. So what we've done here is given the user of choice, you can, if we set this choice here to moderate, the first 2 or 3 steps of the optimization, it will apply a fraction of the correction that it computes rather than the full correction. So you can see here the first correction was pretty small. And the next one also. And now I think it's going to apply the full corrections. And we're done. And clearly we're very close to a perfect equal ripple response across the passband with 20 dB return loss. So in following videos, we'll do some more challenging examples with the optimizer.